In this section, we're going to look at interference of light. Two waves are said to interfere if they meet at the same point at the same time. So you can say interference is the meeting of two, or you can say or more, light waves at the same point at the same time. At the same point at the same time. Okay. So let's say you've got a wave coming over here, another wave coming from here. If they meet at the same point, we say the two waves interfere. All right. Now, the effect of the interference of two waves is the algebraic sum of the two waves. For example, let's say one of the waves is given by y1 equals a1 cosine omega t minus kx1. Let's say y2 is a2 cosine of omega t minus kx2, like this. Then the net effect of these two waves is simply the sum of the two waves. So y net, the net wave, is simply the sum of y1 plus y2. So the net wave is simply the algebraic sum of the two waves. The net wave is the algebraic sum of the two waves. But if you just look at the amplitudes, the amplitudes are actually added like vectors. So we're just going to look at two extreme cases: constructive interference and destructive interference. Okay, so let's look at constructive interference. Constructive interference is interference with the maximum possible effect. This is interference with the maximum possible effect. In other words, is interference where the net wave has the maximum amplitude. Okay, this happens when the two waves are in phase. It happens when the two waves are in phase. Okay, we say two waves are in phase if they're oscillating together. You see, let's say we have these two waves. You may have this one wave, another one, you see, reaches maximum and minimum at the same time, like this. You see, if they reach maximum and minimum at the same time, they're said to be in phase. Okay, so we'll have the maximum effect when the two waves are in phase, or when the phase shift between the two waves is 0 or an integral multiple of 2 pi. Okay. Two waves are in phase. When the phase shift between the two waves, is an integral multiple of 2 pi. An integral multiple of 2 pi. Okay, so two waves are going to be in phase if the phase shift is 0, 2 pi, 4 pi, negative 4 pi, and so on. Okay, so we can say, let's say this stands for phase shift. then two waves will be in phase if delta n is equal to n times 2 pi, where n is an integer, where n is an integer. In other words, delta n refers to negative 4 pi, negative 2 pi, 0, 2 pi, 4 pi, and so on. So two waves will be in phase if the phase shift between the two waves is an integral multiple of 2 pi. So this is the condition of constructive interference. Okay? So the condition for constructive interference is that the phase shift between the two waves is an integral multiple of 2 pi. All right? And then we have destructive interference. This is interference with the minimum possible effect. This is interference with the minimum possible effect. Minimum possible effect. Okay, so there's interference with the minimum amplitude, where the net wave has the minimum amplitude. Okay, it happens when the two waves are out of phase. It happens when the two waves are out of phase. Okay, we say two waves are out of phase when they oscillate in opposite directions. Let's say this is one of the waves. Okay, if the other one reaches minimum and the other reaches maximum, and so on, this is what you call out of phase. In other words, they will cancel each other. Okay, so the amplitude of the net wave will simply be the difference between the amplitudes of the two waves. All right, this happens when the phase shift between the two waves is an odd integral multiple of pi. Okay, two waves will be out of phase when the phase shift between the two waves is an odd integral multiple of pi. That is pi is 3 pi, 5 pi, negative 3 pi, and so on. So the condition of destructive interference can be written as delta n equals 2n plus 1 times pi, where n is an integer. Okay, so basically this means delta n refers to negative 3 pi, negative pi, pi, 3 pi, and so on. Okay, so two waves are said to be in to interfere destructively if the phase shift between the two waves is an odd integral multiple of pi. Okay, so two waves interfere constructively if the phase shift in the two waves is an even integral multiple of pi. That's 4 pi, 2 pi, 0, 2 pi, and so on. And they interfere destructively if the phase shift in the two waves is an odd integral multiple of pi. Let's consider an example. Determine whether the following pairs of waves, interfere constructively, destructively, or neither. Okay, so A, let's say one of the waves is y1 equals, let's say, 4 cosine omega t minus let's say pi over 2. Okay, and the other one is y2 equals 5 cosine of omega t, maybe let's use numbers over here, 10t minus 5 pi over 2. Okay, so phase shift is the difference between the phase shifts of the two waves. This phase shift is, you can say, beta 2 minus beta 1. So in this case, beta 2 is 5 pi over 2 and beta 1 is pi over 2. Okay, so the phase shift in this case, the phase shift delta is 5 pi over 2 minus pi over 2. Okay, that is 4 pi over 2 or 2 pi. Okay, so this is an integral multiple of 2 pi, therefore it follows that these two waves interfere constructively. So this is constructive interference. Constructive interference, because 2 pi is an integral multiple of 2 pi, that is 1 times 2 pi. All right. B, let's say we have the following waves: 2 cosine of 20t, let's say minus pi, and then y2 is, let's say, 3 cosine 20t minus let's say 4 pi. Okay, so in this case, beta 2 is 4 pi, beta 1 is pi, so the phase shift, which is beta 2 minus beta 1, is 4 pi minus pi 3 pi. This is an odd integral multiple of pi, therefore it is destructive interference. Destructive interference. Okay, C, let's say we have y1 equals 6 cosine maybe 30t minus pi over 2, and let's say y2 is let's say 7 cosine of 30t minus, let's say, 3 pi. Okay, so in this case the phase angle for this one is 3 pi, the phase angle for the first one is pi over 2, so the phase shift is beta 2 minus pi over 1, that is 3 pi minus pi over 2, that is 5 pi over 2. So in this case, this is not an integral multiple of 2 pi, so it's not constructive interference. It's not an odd integral multiple of pi, so it's not destructive interference. So this one is neither. Neither. All right. Now we're going to express the conditions of constructive and destructive interference in terms of path differences. Okay, expressing the conditions of constructive and destructive interference in terms of path differences. Okay, path differences. We're going to use delta for path difference. Okay, so path difference is the difference between the distance traveled by the two waves. Let's say these two waves, one of them starts over here. Let's say it travels a distance of x1 over here, and then another, let's say, starts over here, so it travels a distance of x over here. So the path difference in this case is, the delta would be x2 minus x1. That is the difference between the distance traveled by the two waves. So we want to express the conditions of destructive interference and constructive interference in terms of this path difference, the difference between the distance traveled by the two waves. Okay. Now suppose you have the following two waves. This is a1 cosine omega t minus kx1, okay, and then y2 is a2 cosine of omega t minus kx2. Okay, so in this case, the path difference delta equals the phase angle of the second one minus the phase angle of the first one. That is k x2 minus x1. Okay, so this one is the path difference delta. Okay, sorry, this is the phase difference. So you've got the phase difference is k times the path difference delta. But if you remember, k is 2 pi divided by the wavelengths. Okay, so the relationship between the phase difference and the path difference is delta equals 2 pi over lambda times the path difference. In other words, the path difference equals the phase angle times lambda, delta equals times lambda over lambda over 2 pi, this lambda over 2 pi. Okay, we're just cross multiplying over here. All right, now let's go to the conditions. Let's start with the constructive interference. Constructive interference, the condition is delta n equals n or integral multiple of 2 pi where n is integer. Okay, now you see over here, delta is the phase difference times lambda over 2 pi. Okay, so we have delta n equals, you see, lambda over 2 pi, lambda over 2 pi times delta n, right? But delta n equals lambda over 2 pi, delta n equals n 2 pi, right? So 2 pi cancels out, so we've got lambda n equals n lambda. Okay, so in terms of path difference, the interference will be constructive if the wavelength is if the path difference is an integral multiple of the wavelengths. So the condition of constructive interference is that constructive interference takes place when the path difference is an integral multiple of the wavelengths, is an integral multiple of the wavelengths of the light, That means the constructive interference takes place when this is negative, let's say 3 lambda, negative 2 lambda, negative lambda, 0 lambda, 2 lambda, 3 lambda, and so on. Okay, so constructive interference takes place when the path difference between the two waves is an integral multiple of the wavelengths. All right, now let's look at the condition of destructive interference in terms of path difference. Destructive interference in terms of path difference. Okay, again, the condition for destructive interference in terms of phase difference is this one, to n equals an odd integral multiple of pi where n is an integer. Okay, Now we have the following relationship between delta and the phase difference. Delta n equals lambda over 2 pi times the phase difference n. Okay, so we have the following formula. This equals lambda n over 2 pi times the condition for distractive interference, which is over here. Which is this one over here. There's a condition for distractive interference. So that is 2n plus 1 times pi. Okay, so that means delta n equals lambda n over 2, and then the pi goes away, so you've got 2n plus 1. Okay, so if you divide by 2, you've got lambda n equals n plus half times lambda n. Okay, so you see, distractive interference takes place when the path difference is half of odd integral multiples of the wavelengths. What this means is delta is when n is 0, you get lambda n over 2. When n is 1, you get 3 over 2 lambda. When this is 3, you get when this is 2, you get 5 over 2 lambda, and so on. Okay, same direction, the negative direction. All right, so distractive interference takes place when the path difference is half of odd integral multiples of the wavelengths. Okay, so the conclusion is distractive interference takes place when the path difference is half of odd integral multiples of the wavelengths. Okay, so this is a condition for distractive interference in terms of path difference, that is the difference between the distance traveled by the two waves. All right, maybe finally let me put those conditions together. So the conditions of constructive interference in terms of phase shift, it is n times 2 pi, n integer, and in terms of path difference is delta n equals n times lambda. Okay, that is integral multiple of the wavelengths. All right, n integer. I don't think we need this one over here. Let me take this one out. Okay, so these are the conditions of constructive interference. The first one in terms of phase difference, and second one in terms of path difference. All right, and then the conditions of distractive interference. Conditions of distractive interference are in terms of phase shift, it is n times 2 pi, or n is integer, and in terms of path difference, it is n times lambda. Okay, again, an integer. So these are the conditions of distractive interference in terms of phase difference and path difference, and these are conditions of constructive interference in terms of phase difference and path difference. All right, now we're going to look at an experiment called Young's double slit experiment. But before that, let me define what we mean by diffraction of light. Diffraction of light, this is the bending of light as light crosses an obstacle. This is bending of light as light crosses an obstacle. Now we know light travels in a straight line. Suppose you have this barrier over here like this, and you've got light coming this way over here. Now when it's on the other side, okay, if light travels this line, you will expect to see light over here, but what happens, some of the light will bend, so you'll see light actually in this region over here because of the bending of light. When it crosses an obstacle, this obstacle, some of the light rays will be bent, so you will see light on this side even though there's a barrier over here. The reason is because light bends when it crosses an obstacle. Such a process is called diffraction. Diffraction is the bending of light as it crosses an obstacle. Okay, now we're going to look at an example of interference of light, which is called the Young's double slit experiment. So let's look at Young's double slit experiment. Young's double slit experiment. So in this case, what we have is we have a barrier with two slits over here, okay, two slits, and then we have a source of light over here, okay, and then we have a screen over here, So as light comes over here like this, what happens is when the light crosses this obstacle, the light rays bend, they go everywhere, okay, they go everywhere like this because of diffraction. And then when light comes over here, you see at this obstacle, the same thing happens. Light goes everywhere. So what we have on the screen is the interference of, all should come from, sorry, all the lights coming from here. Okay, so what happens on the screen is the interference of a light coming from slit and light coming on the slit. All right, so we're going to see interference pattern over here. So let's see the conditions for distractive and constructive interference. All right, now let's take this point over here. So you got light coming from here, and then let's say we have light coming from here. Okay, so let's drop the perpendicular over here. This one over here is the path difference delta. Okay, that is the difference between the distance traveled by the two waves, this distance over here. All right, now if this angle is theta and this separation with the slits d, we can see that delta equals the separation with the slits d times the sine of the angle theta. Okay, now for constructive interference, we know the condition is that the path difference is an integral multiple of the wavelengths. Therefore, the condition for distractive interference in this case is d sine theta equals n times the wavelengths. Okay, so this is the condition for constructive interference. That is the condition for getting a bright spot over here. All right, so this is condition for constructive interference or bright spot. Constructive interference or bright spot. Okay, so we're going to have constructive interference when this expression d times sin of theta equals, let's say, negative 2 lambda, negative lambda, 0 lambda, 2 lambda, and so on. Okay, and for destructive interference, the condition is delta n equals n plus half times the wavelengths, right? But our path difference is d sine theta, right? So that equals n plus half times the wavelength. So this would be the condition of destructive interference or dark spots. This is condition of destructive interference or dark spot. Okay, that is when this expression equals, let's say, negative 3 over 2 lambda, negative lambda over 2, lambda over 2, 3 lambda over 2, and so on. We'll see a dark spot. Okay, now let's go back to the experiment. We have this double slit barrier over here, and then we're going to have an interference of light coming from here and from here. Now the center over here, between these two over here, the path difference will be 0. Okay, the distance traveled by these two waves will be equal to the center. So we expect, since the path difference is 0, we expect a bright spot. So we're going to have a bright spot over here. But then next, you see, as you go farther, the path difference will increase. Next one comes half of the wavelengths, that's darkness, okay? And then full wavelengths, that is brightness, darkness, brightness, and so on. You see, we get darkness for the half wavelengths, lambda over 3 lambda over 2, and so on. And we get brightness, which is this amplitude over here, for the integral multiples of the wavelengths. Okay, so this is a pattern we'll see on the screen. We'll see alternatively brightness and darkness, brightness, darkness, brightness, darkness, and so on. Now the number n is called order. This is order. So you see, this is the n equals 0 over here. Okay, and then of course we have n equals 1, n equals 2, and so on. The same thing on the other side. We'll have n equals 1, maybe n equals negative 1, n equals negative 2, and so on. Okay, so n is called the order of interference. This is the order of interference. Okay, so what we have is, we have a light source over here. You've got slits over here. The slits will act as the source. You've got light coming from the slit and the interfere over here, and we see interference pattern. And using the conditions of constructive interference, it follows that we'll have bright spot when this path difference over here, which is equal to d sine theta, is an integral multiple of the wavelengths, and we see bright spot when this path difference is half of or integral multiples of the wavelengths. So the phase difference starts with 0 at the center, which is constructive interference. Then as we go farther, you see the path difference increases. So first we get half of the wavelength, which is darkness. Next we get full wavelength, which is brightness. And so we see alternatively brightness and darkness on the screen. That is the result of the double slit experiment, the result of waves interfering from two slits over here. Okay, the interference for wave coming from here and a wave coming from here results in this kind of pattern of brightness and darkness. Example. In a double slit experiment. In a double slit experiment, the slits are separated, let's say by a distance of, let's say, 1.5 times 10 to the power of -6 meters, or 1.5 micrometers. Okay, if the second order bright spot occurs, let me say first, the first order bright spot occurs at an angle of 20 degrees, calculate the wavelengths of the light, Okay, so this first order, n is 1. We're told d is 1.5 times 10 to the power of -6. Okay, and this occurs when the angle is 20 degrees, theta is 20 degrees. So the question is calculate the wavelengths of the light. Okay, so this is a bright spot, so you gotta use the condition for constructive interference, which is d sine theta equals n lambda. Okay, so we have 1.5 times 10 to the power -6 times the sine of 20 degrees equals the first order times the wavelengths. So the wavelength simply 1.5 times 10 to the power -6 times the sine of 20 meters. Okay, so that'll be the wavelengths of the light.